Okay, let's move on to the next part of this MOSFET lecture, which is on MOSFETs for memory. And so we're going to look at three types of metal oxide semiconductor memory devices. We're going to look at DRAM, SRAM, and flash. And again, we don't have to do a whole lot of new physics understanding because we've already covered MOSFETs in details, and these are all just based on MOSFETs. Sorry, that was a brief interruption. Okay. So, let's look at the first one here, which is Dynamic Random Access Memory, or DRAM. And so here's some of the key features for this. You basically read or write any bit in what's called a 1C, 1T cell. That means one capacitor, one metal oxide semiconductor capacitor, and one metal oxide semiconductor transistor. And so the capacitor is just the gate, the metal, and the channel, but without the source and the drain. So it's just a capacitor that you could charge up. The T is the MOS transistor, meaning it's got a source and drain and it could get current flow through it. So when you look at this, here's one cell, a 1C, 1T cell, where here's the MOS transistor, and then here's the capacitor, which is just the gate of a MOSFET without the source and the drain. So you could just charge it up like a capacitor, discharge it. Okay? So how this works is the row electrodes can turn on an entire row. So for example, I could put voltage on this row here, and the voltage would turn on the gates for all of these transistors, and then while that row is turned on, I can send data up the columns to charge the capacitors to a 1 or a 0. So for example, I could set the capacitors to 0 volts for a 0, or I could set the capacitors to 5 volts for a 1. As soon as I'm done with that, I will turn the voltage off to these transistors, and then storage on this capacitor is isolated from the line. So this goes off, and I can keep the charge on the capacitor. So how I do this, if I want to write all the memory, is I'll do the first row, turn these all on, send all the data up to the capacitors. I'll do the second row, the third row, the fourth row, each row one at a time, writing the data through the transistors to the capacitors. Now, some of the challenges with this type of RAM, dynamic random access memory, is that this MOSFET doesn't have infinite resistance in the off state, right? It still has some leakage current even in the off state. And so this capacitor will discharge in a period of milliseconds. Now you're like, milliseconds, that's pretty fast. You know, in computing terms, that's not fast at all. We're talking gigahertz, which is nanoseconds for computing terms, which is 1,000,000 times faster than milliseconds. And so that's pretty long, but that's still short enough that every now and then you're going to have to refresh all the 1 and 0 states on all these, because if you don't, they'll all leak back to 0. And so you have to constantly refresh DRAM to all its data values for these capacitors from time to time, which is a bit of a disadvantage. However, it's pretty simple. So that's one of the big advantages of DRAM. You can see this is probably pretty easy to make. So the question is, why do we have SRAM and flash? Well, one of the reasons we'll have SRAM and flash is in those technologies we don't have to refresh the memory once it's been written. So let's take a look at those and we'll start to get an appreciation for them. So let's look at SRAM, static random access memory, and here's some of the key features here. Okay? And so what you have, this is one SRAM cell, it's more complicated. You can read or write any bit in a transistor cell, which consists of 2 cross-coupled inverters. And so if you look at this, I'll try to highlight this. Here's one inverter here. Okay? Here's another inverter over here. See the inverter? Okay, there's the PMOS, there's the NMOS. So I've got an inverter here and an inverter here. They're cross-coupled, meaning that for this inverter here, its output couples to the input of the other inverter. So the outputs couple to the inverts of the outputs couple to the inputs of the other inverters. And so the beauty of this and why this works well is if I were to charge, let's say I basically get this set up to the state where I have a 1 here. Well, a 1 goes through an inverter and becomes a 0, right? A 0 goes into this inverter and becomes a 1, which reinforces the original 1. And so once you lock this into a state of a 1 or a 0 on one inverter, the other inverter reinforces that. And so you can latch it into one state or another. For example, if this was a 0, I'd get a 1 here, a 1 here, becomes a 0 here, which reinforces the 0 I had. Okay? How this is written is what I'll do is I'll put a voltage on my word line to turn these transistors on, and then I'll bring enough data up my bit lines. Okay, this word line's like my rows, this is like my columns. I'll bring data up the bit lines to overpower the inverters and set them into a new state. So this will be a bit line value, this is the inverse of the bit line value, and I will overwrite the outputs here. So latch it into a new state. Once I've done that, I'll turn these transistors off for the word line, and this thing will stay coupled into its logic 1 or logic 0 state. Now, so one of the advantages of this is that once I've set this, it stays. I don't have to refresh it. Another big advantage of this is that when I want to read my 1 or 0 out, I could turn this on and turn this on over here, not try to put a voltage to force this into a new state, but rather just let the voltage supplied by these allow me to read out the value on the bit lines. And the advantage of this is this readout is actively driven by transistors which are powered. And so before with SRAM, I had that little capacitor, right? And that capacitor had a little bit of charge on it, and it goes through the transistor, and it's got to basically charge up and get the signal out this really long line out that goes out the memory chip. Well, you could imagine that that might not be very fast, or it would be weak, because once the capacitor runs out of charge, that's all the charge you have to try to read out of the system. In this case, I have a powered transistor driving the charge onto the line, which is more powerful and can be faster. And so I can get faster speeds with this. And so that answers the question why we would have DRAM and why we would have SRAM. Okay? So the question is, if SRAM can be a little bit faster, and if SRAM doesn't have to be refreshed, why do we have DRAM? Well, you can see that here and here. Here is the SRAM cell. It's more complicated. And if you look at a SRAM cell in terms of actually fabrication here, here's a 6T SRAM cell, meaning that it requires 6 transistors. 1, 2, 3, 4, 5, 6, right? The question is, can SRAM be high density or as high density as DRAM? Well, of course it can't, because DRAM, we had 1 C, 1 T, 1 capacitor and 1 transistor. Very small. For SRAM, you've got 6 transistors. And so your density of memory you can achieve is less. And so although SRAM can be faster and doesn't have to be refreshed, you're not going to get the memory of density and the maximum storage for one chip as you would have with DRAM. Let's look at the third memory, flash. Okay? So it's somewhat like DRAM, except the control gate can force charge from a channel into the floating gate. Okay, so here's how this works. So I have a transistor here, and I have a gate, but I also have a control gate and a floating gate. Okay? How this works is that I'll put a voltage on the drain to source such that I can get current flow through here. And then I'll put a voltage on the control gate to basically try to get inversion to allow current flow from drain to source. But what I'll do differently is I will inject charge into the floating gate, which puts an offset voltage into the input voltage. And so I could have either a little bit of starting voltage to lower threshold voltage, or a little bit of starting voltage to increase threshold voltage by injecting charge in here, which offsets my starting position. Therefore, the amount of current I will get out of this will be much different whether or not I have charge stored and trapped in the semiconductor between these two oxides. So the question is, well, how do I get the charge in here? Well, it's actually really elegant how they do this. What they'll do is they'll put a high voltage on the drain, and so they'll put a significant voltage on the drain, and they'll make it high enough that the electrons get accelerated to really high energies. So the electrons are accelerating across here. I get inversion. They're accelerated to really high energies. Remember when we had tunneling? We said for a tunnel barrier, there are two ways to get through the tunnel barrier. One, the tunnel barrier can be thin and an electron could go through it, or the electron could get enough energy to go over the tunnel barrier. Well, this oxide here is like a tunnel barrier. If we use enough voltage across here to get the electrons accelerated to high energies, they will have enough energy to jump over this tunnel barrier and start charging up this floating gate here, which will then offset my external voltage and give me a different current value depending on if it's a 1 or a 0. The nice thing about this is once I've trapped this charge in here, it's stuck here, and so I don't need to refresh this thing. I can write this typically in only a time of about a microsecond. Okay? And so you've got a way to basically make a storage device where it will hold the memory indefinitely, and then when you want to read it out, you basically put your voltage on drain to source, and you see how much current you get for a given gate voltage. You don't have to erase this in the process, and it'll tell you whether or not you had charge there or not, and whether or not it was basically a flash bit that was in a 1 or a 0 state. So, let's talk about some of the limitations here. Okay? So, you're typically limited to millions of cycles before this starts to degrade, because basically if I'm putting a high current level and I'm getting high energy electrons, some of those electrons have enough energy that they can damage my oxide layer. So this oxide layer over time will start to degrade as I try to force electrons from one side to the other of it. Okay? And so you could typically write this, millions of times. So that's a limitation. One of the advantages of this is that this is just one transistor to store a bit. How beautiful is that? Meaning that I can get very high density memory on a chip. That's why flash drives can get such high densities, because each bit just requires one transistor like this, where it's got its storage and its transistor readout all in one device. Okay, so you get large memory capacity. So why do we use DRAM and SRAM for processing data, but we don't use flash if flash is so nice? Well, think about it this way. If you used flash for 1 gigahertz processing, how long would it last? How long would your flash microprocessor last? Well, if I could only write this thing millions of times before it degrades, and I'm running this thing at 1 gigahertz, which is 1 billion times per second, then that means that my flash microprocessor would last 1 millisecond before it burns out. And so flash is great for storage, where you store it, and then you're done, and you wait a while before you use it again, and you'll never use it more than 1 million times. But you never use it for processing, because you would just burn through the number of storage cycles very quickly and burn the chip out in about a millisecond. Here's a nice diagram from the book showing how you get the charge into the floating gate here. And so here's the oxide, here's the channel. And what they're showing here is that here's my channel. I've got inversion. So this is the opposite as we normally look at it. Here's my channel, here's my floating gate, here's my oxide. So it's reversed left to right compared to how we normally look on it. I get enough band bending that I get inversion here. And I accelerate my electrons at high enough speeds such that they start to exist at higher energies in the channel. If I accelerate them to high enough energies, they could be up here, and they can then get over the barrier and start to deposit in the floating gate. So the question is, okay, once I've got the electrons in the floating gate in here, how do I get them out? Because I need to basically write and erase this type of memory. Well, I'll put the opposite voltage on the gate. So in this case, I'm putting 0 volts here, 12 volts here. So that would be making negative charges go in this direction. Okay? And I'm specifically going to try to erase it right here. So right here, I get 12 volts across this. Positive relative to this, positive this side pulls the bands down, right? So this pulls it down, this goes up. If I get enough voltage, I can basically get this barrier here to be small enough that I get tunneling of the electrons through this short barrier here, and then they're on their way to go on to the source. So instead of having the tunnel through the full thickness, which would be through the full thickness of the oxide, you put enough voltage that the barrier reduces to this area, and then I can get tunneling through the barrier. Here's a ID versus gate voltage characteristic for a flash memory type device. Here's the array state, here's the program state, and it says it down here. It says if it's in the low VT state like it is here, the MOSFET is turned on, and that is a 1. So that's a logic 1, meaning that basically here's the read voltage. I set my read voltage right here. So I'll set my read voltage to this, okay? So I put that on my gate, the outmost portion of the gate, and if I had set the charge inside that floating gate such that the threshold voltage is lowered, then when I put my read voltage, I will get current out. So this would be a logic 1. If I put the charge on the floating gate such that it increases the threshold voltage, and then I do my readout voltage, my current, you can see, is 0. And so that would be a logic 0. Now, to help flash memory last longer, people are doing some interesting things. This is a press release from Micronics where they're basically building in a heater which they can fire up above the memory. And what they do is after the oxide's been damaged by multiple write cycles, they heal it by heating it up to 800 degrees Celsius for just a few milliseconds. That's hot enough and long enough that it can repair the oxide. It's kind of not remelt it, but it kind of helps the bonds reform in the oxide and helps it form a high quality oxide again, and then allows it to repair itself. So then you can use flash memory more often and extend its lifetime. Here's a DRAM cross-section. So this is the DRAM, Dynamic Random Access Memory, not SRAM. This is the one that has the 1T and 1C cell. 1T, one transistor and one capacitor. So if you look at this, here's the transistors are down here. Okay, so here's one cell. It's got one transistor down here with the source, a drain, and it's got a source and draining gate. I'm not sure where they are looking at this. And then the capacitors are up here. And so my question is that when they have these cells, why do they put the capacitors up here and the transistors down here? Why don't they put them side by side? Why do they have to go through all this effort to stack them on top of each other? Well, it's simple. If you make a computer chip, and I want to basically have as much memory as possible on one chip, if I put my capacitors next to my transistors, that would take twice as much space on the chip as if I put my transistors and capacitors on top of each other. So for this type of configuration, like I have here, capacitors on top of the transistors, I can get much higher density memory for a given chip. I can get more data storage. Here's a 1 gigabyte 48 nanometer DRAM cell. So that's 1 gigabyte, 10 to the 9th storage bits. And you can see they're showing where the word line is and all the other things as well. But here's the amazing thing of this. When you scale down to and they make these things as small as possible, you can see that these wires look like they're almost touching each other. So the question is, there's a billion of these. Can any of them fail? The answer is no, that you know that for a given chip you cannot have any failures. So it's pretty amazing when you actually start to fabricate these things and make the cells and keep them isolated by these tiny little separations. They can do it perfectly such that there's no electrical shorts for a billion of these things. So obviously semiconductor manufacturing, there's a lot of money invested in it to make it work as good as it does. And others are working on technologies to even upend flash, DRAM, etc. This is a company called Crossbar that's taking on DRAM and flash storage with something they call long-lasting RRAM. Okay? That's a resistive random access memory. I'm not going to go over how it works, but they can get very high densities and stack them up vertically. And here's the key point. They show that here's a competitor's solution of memory, here, 8 gigabytes, and then here is the size if you use Crossbar's 8 gigabytes. So it's the same story. Give me more memory capacity per chip size. So instead of giving, this is more than double of that. So if I had an 8 gigabyte module, this with the same area of chip would be a 16 gigabyte module. Okay, again, take a break and we'll get to the next one, which will finish off this lecture.